Again, we start off with the same assumption. We have a set of three vectors, x, y, and z this time. Again, I will assume that they are linear dependent. I'll try to establish some sort of geometrical properties which bind these three vectors. So first I will spell out the definition of linear dependence. It means that if there are three coefficients for which I use Greek letters again, lambda, mu, and I need a third one, nu, I can be sure that one of them is not zero. That's exactly what this line says. And I can be sure that with those coefficients, if I compute a linear combination of my three vectors, it will be zero. This is the spelling of the linear dependence definition in case of three vectors specifically. Now we will do the same procedure. We will analyze this individually. We'll just say what happens if lambda is not zero. Again, I can solve in that case for x. And what I see, x is a linear combination of y and z with these specific coefficients. If it is the mu, which is not zero, then I can solve for y. And then my y is a linear combination of x and z. If it is nu, which is specifically not zero, then again I can solve, and I can solve for z this time, and z will be a combination of the other two vectors. What are the geometrical interpretations of these three relations? And when we discussed with you the case of two vectors, we had this one scalar multiple of the other, and we know what that means in geometric terms. That means that the vectors are parallel. What do we know about the geometry of the vectors, of three vectors, such that one of them is a linear combination of the other two? Just pay attention. I'm referencing this right-hand side as a linear combination, which is a true thing. Two vectors combined with two coefficients, I should say. What's the geometrical interpretation of this fact? The interpretation is that my three vectors belong to one single plane. The term is coplanar for that. In either of these cases, these relations, geometrically, they mean that my three vectors, they come from one single plane. They sit or belong to one single plane. The term is coplanar. It's like parallel for two vectors. For plane, it's a coplanar. And that's the geometrical interpretation of this fact. This is if and only if, again. I mean, if you assume, in my argument here, I assume that my vectors are linear dependent, and I delivered that vectors are coplanar. You can do the opposite way. You can assume that the vectors are coplanar and prove that they will be linear dependent. It's a very simple proof. It's a one-liner again. It's like with the parallel. You start off with the assumption that one vector is a linear combination of the other two, rearrange the terms into a linear combination, and you will have one non-zero coefficient. If you start off with the assumption they are coplanar, it means that one vector, say bfx, is a linear combination of the other two. I will use, say, alpha bfy plus beta bf, like this. I use different letters for the coefficients, and then you can rearrange. Like before, you can say explicitly, you can say explicitly the coefficients. Plus minus alpha y plus minus beta. Here it is. This is the argument which does it in the other way. If your vectors are coplanar, one of them is a linear combination of the other two. You can rearrange into linear combination like this, and you can see here linear combination being zero, even though not every coefficient is zero right here. Very explicit coefficient which is certainly not zero.